Okay, we're going to do a problem on finding temperature, basically with our activation energies, and how to calculate the temperature at which a rate constant is at a certain point. So we'll begin. I have written the question out already just so we can go ahead and start on it. The rate constant of the first order reaction is 2.55 times 10 to the negative fourth per second at 350 degrees Celsius. If the activation energy is 155 kilojoules per mole, calculate the temperature at which the rate constant is 7.45 times 10 to the fourth seconds per second. Now, we have things in Celsius over here, so I wrote down the conversion factor for us to follow so we can just go ahead and get on with it. So, we have here 350 degrees Celsius for right here, plus 273, which is just a constant on which how to find the Kelvin, because in these equations we need to work with Kelvin, which we calculate here. And let me go ahead and punch that into my calculator. You could do it really quick in your head, or you can just click these nice fancy buttons. And this equals out to 623, and then of course 0.15, and that's Kelvin we're working with. Now we have the regular first order reaction. The equation right here, but I went ahead and I formulated it in the way that would actually work in our favor, so we can find what we need to find fairly quickly. So from here, so this was rearranged. So from here we can go into actually converting our activation energy into kilojoules. So usually I just move the point, but for this video I'll go ahead and just do the full equation conversion, joules over 1 kilojoule. So see, just cancel this. Now it's going to be joules per mole, so that would equal out to 155,000 joules per mole. And then we use the Arrhenius equation to solve for T2 to find the temperature. So from here, T2, can you see, is equal to, let me switch colors so we can see, our gas constant, or I'm sorry, our gas constant, but it's a for power usage only. 4 and joules over mole per Kelvin, all over 155,000 joules per mole. Note, when we do cancel out things, all these units will be removed for the most part. And then we put in our 2.55 times 10 to the negative fourth per second over 7.45 times 10 to the negative 4 per second. See how things kind of cancel out. Plus 1 over, and then the 623 where we got from up here, we're just going to put down here. Because the way the algebra works is that we move everything around so we can actually find what we're looking for. Now from here, we will be just plugging into the calculator. You have the option of plugging into the calculator in hunks, basically. So personally, I would do this one first by itself, and then natural log of all this together, and then I would multiply the natural log by this. And then 2 is equal to, I've already solved the equation, 646.15K. Now, this isn't our final answer. What we need to do is we need to convert it back to Celsius. So to do that, instead of adding, we will actually subtract. So 646.15K is minus 273.15. And that is equal to 373 Celsius. And there we go. That's how you would do the problem to find the temperature for the rate constant at this particular point.